Welcome to this video on an introduction to RC circuits. Here, RC does not stand for remote control, actually resistor capacitor circuits. And so over here, from the awesome FET simulations, this is one of their older simulations that's not HTML5 just yet. So I've included it here so that you can take a look at an RC circuit and how that would function. So the RC circuit has a resistor and a capacitor as its two primary circuit elements. Now mine look a little bit, my circuit looks a little bit more complex, but that's purely for the need of time and experimentation here that I've designed it the way that I have. So let's go ahead and, as a good review, draw the circuit in circuit schematic form. So I have a power supply or a battery at top here, and then I have a resistor over here on the side. I have a capacitor down here. I then have an ammeter, which I'm going to use to measure the current. Okay, we'll skip that middle branch for a second here. We'll then have a switch, which is currently open. And then the way that I've designed it is with this switch here in the middle branch that basically is only there so that I can discharge this capacitor once it's been charged. So I see I have two primary loops here that I'm going to use. This outer loop, which will close the circuit to charge the capacitor, and then the inner, or this bottom loop over here, which I will then reopen the outside loop and then close the inside loop to discharge the capacitor. But the primary idea is that I have a resistor and a capacitor here. Now when we first started learning about capacitors and we connected them to a battery, we technically had a capacitor circuit. There wasn't a resistor capacitor circuit, but we did see that there was effectively a little bit of time dependence. So all the other circuits we've looked to up to this point, where we've looked at resistor circuits, those resistor circuits had a steady state current. In other words, the current was not changing as time passed. But now we will see that the time will have an effect on how much current is flowing through the circuit. And that's what we're going to take a look at here in this video. So let's start by charging the capacitor. I'm going to close the outer loop circuit. This inner loop will of course not matter because the switch is open, but I want you to take a look at the current here and what's happening to the current as time passes. So we see here we had an initial current value and now it's dropping, slowly approaching zero. Now would be a good time, if you want, to pause the video and try to come up with, some descriptions of what's happening here. And then I'll reset it and we can take a look at it again. So the first thing that I notice is that as soon as the switch is closed, when t equals 0, I'll go ahead and write this out here. When t equals 0, the current is some maximum value. So I'll say I initial is the current maximum. So it's this initial value that it's its highest value. And then I'm going to say when time is equal to infinity, because I didn't actually measure the time, but right now at this point we can see that the current is equal to 0 amps. Another thing that I noticed was that this was a non-constant decrease in the current. So the current as time passed was decreasing but at a non-constant rate. So let's go ahead and we'll make a graph here of current versus time. We're just sketching a graph here, so we have current in amps and we have time, I'll do it in seconds. So we have an I versus T chart. And what we're going to say is that there was an initial value for the current when time equaled 0. And then when time equaled infinity, I said the current was effectively 0. And so if I actually plot this, I have a y-intercept, and then this function approaches 0, or an asymptote that is approaching 0. So we have something that looks somewhat like this. Now let's see what happens when I discharge the capacitor in terms of the current. So I'm going to open this outer switch so as if the battery branch here was not at play. And I'm going to close the middle switch. And we see essentially the same thing happen. So the same thing basically happened. So I'll go ahead and I'll charge the capacitor up again. and then as soon as it's fully charged, we'll open this and discharge it. And we're seeing essentially the same thing happen. And it looks almost like it's the same amount of time as well. So what we could say that this is the I versus T graph for charging, but also for discharging the capacitor. They look approximately the same, at least from this perspective. Now, there may be other things at play here that we're not paying attention to, but we will take a look at that and see how to make the fine adjustments later on. Okay, now the big thing about RC circuits is that the resistor matters just as much as the capacitor. We're going to take a look at the resistor here in a second. So let's go ahead and change the resistance of this resistor. So I'm going to change the resistance. It's currently 10 ohms. I'm going to go ahead and make it 75 ohms. So there we have now a 75 ohm resistor. I'm going to open the middle switch. I'll close this outer one and let's see if we can compare what happened. Well, the first thing I'm noticing is that it's taking a lot longer to reach the zero current value. So this graph is going to be less sort of steep approaching zero. In addition, it didn't start at as high a current as this initial one did, which makes sense because I have more resistance. And so in a series configuration here, the greater the resistance, the lower the current should be. So let's go ahead and reset the dynamics and see what it started at. It only started at about 1.2 amps. So that's one thing that we could say for sure, that there was a lower value here than there was before. So we'll go ahead and we'll plot that so that we can show. So over here we had a lower initial current value, and this was for the higher resistance. And then it's also taking a lot longer to reach zero. So it's almost as though this graph over here is taking its approach is much, much shallower. So we can see that there is, as I increase the resistance, the time it takes for the capacitor to fully charge is much longer. So let's look at that perspective. Maybe that can be a better way to look at this. Let's see what is the charge on the capacitor, or how is the charge related to the current. So if I were to sketch a graph of the charge on the capacitor plates versus time, so I'll put Q in coulombs versus T in seconds. So Q versus T. What I see is it's reaching a fixed value right here. Now the way that I could probably calculate that is to take a voltmeter, and I will attach my voltmeter across the capacitor, and what we could take a look at here is how quickly, so we'll reset all these values, how quickly this reaches the voltage, the steady voltage. So we see here that this value is changing, and the charge on the plates is becoming more and more and more as the voltage increases up and up and up. So what I can look at here is that essentially what's happening is I'm reaching some sort of an asymptote that's going to go across here on my graph. Now this is in terms of the charge, not the voltage, but I'm using the voltage to show the relationship. So I see it's going to look like something like this, where it's approaching this asymptote, and this asymptote is the total charge across the plates. The voltage is still increasing, the current has stopped. So let's take a look now. As soon as it stops moving, it looks like it's approaching 9 volts. And my guess is this is a 9-volt battery, but let's take a look. This is a very interesting perspective here. So while that's working, I'll go ahead and show the value of this. And yeah, it shows that it's a 9-volt battery. So very interesting. We're getting this point at which the voltage matches the voltage of the battery, which is what we saw before, how it would stop, when it would stop. So if I were going to graph voltage versus time, I might see the same basic shape, obviously not the same values per se. But the total charge that it would reach over here, that maximum value, would be equal to the capacitance of the capacitor times the potential difference that it reaches, right? But as time is passing, that is approaching that point. So we see here we have a variety of graphs that we could use to describe the time dependence of an RC circuit. Let's just quickly take a look at the discharge here. Okay, and it's discharging itself from the 9 volts, and it's all the way, it's approaching 0. And so we might have something during, so this is for charging here, and the discharging is going to look a little bit different. So I'll go ahead and plot that as well. The voltage is still running down. And what we saw was some initial voltage across the capacitor, and it approached 0, somewhat like this. And it's still approaching its 0 point, and the rate is slowing. So we see again, we have this non-constant rate. Now in some subsequent videos, what we're going to do is take a look at how to actually determine what these functions are, and then to look at how the capacitance affects the same variety as the resistance did. So we saw that the resistance increased the time it took to reach its 0 point, and the capacitance may or may not do the same. So we'll take a look at that in the next video.